All right. Practice problems. Woohoo! All right. So in the first case, we have this problem where we want to find the solution of this differential equation. So we want to see how to compute this guy. So here's A, here's B, here's our initial condition, and here's the input that we're going to apply. U is equal to, this is unit step. So that is, in this case, we have a single input system. So this is just a single unit step function. Okay, so that's what the subscript S stands for. It's a unit step. Okay, so A, B, we have as these matrices. So I'm going to go ahead and do this in MATLAB. And in MATLAB, here's the code that I would use. So I would define st and tau as my variables. Okay, as my variables. And so here's A, here's B. This is one way of computing B. And then here's the initial condition that I'm going to work with. I now form Si minus A inverse as my phi of S. I use the inverse Laplace transform, and I let, with respect to S, and instead of plugging in T, I'm going to plug in T minus tau. Okay, so this is going to give me phi of T and tau. So this is what I'm actually getting. Now to see what x of t is, I'm going to assume my t naught is 0, and so I'm going to substitute in for tau 0 times the initial condition plus. So the reason I needed t minus tau is so that when I do this integral, the integral, remember, of t naught to t, e to the a t minus tau. So I needed t minus tau here. So phi of t and tau times b. And notice that since we're applying a unit step function, this is just the value 1. So I just have the value 1 in here. So within the region of this integral. And I'm going from 0 to t. So the unit step function is the value 1 between 0 and t. And so going through and doing all of this, it returns this solution. So this solution then is just a column. There are just two elements. They're functions of time, fairly complicated functions of time. But this is what the solution looks like, x of t, that satisfies the differential equation, the differential equation with this forcing term, this initial condition. So this is what it looks like. This is how the computation. So it's actually instructive to go through and look, for example, at what phi of t and tau looks like. So notice I didn't put a semicolon here so that you can actually see what it looks like in terms of the exponentials. And so here's x of t that we get from this process here. All right. Now, what about linear time varying cases? We've talked about them. What is it? How do we actually work with that kind of thing? So again, we start with a fundamental matrix of solutions given here. And so if we look at this problem, x of t, we said that this is the solution, and again, we can go through and check that, but it's not that straightforward to actually compute something like this. So let's look at an example of how we would compute a problem. So we're going to start with a simple one. So it's simple. It's also a periodic function, so we could actually go through and use flow K-theory. But for now, let's just concentrate on getting the fundamental matrix of solutions. So x dot is equal to a times x. So I can rewrite this equation in terms of its individual equations. Right? So I have the two equations that comes. x1 dot is a function of x1 and x2. x2 dot is only a function of x2. So notice that this second term here is simple in that it is actually a linear equation. So we already know the solution to that equation. Okay, so we then need to, we will use the solution in this equation in solving this equation. Okay, so we know that x2 then can be written in this form. So notice that if I think of this as a state model by itself with the matrix A as 3 and no input, then the solution of this is x2 is equal to e to the minus 3t times x2 at 0. Okay, so I can actually just solve this using the theory, but I don't have a forcing term, and it's very easy to compute because a is just a scalar in this case. It's just a scalar value minus 3. So we get this as our solution. And so now we want to solve this equation, which is dependent upon x2. And so this equation actually is very close to a linear function if I treat this as an input term. Okay, then I have actually a linear equation where this is an input term. So the first equation is linear time invariant with the time varying term. And so again, we can treat this using the theory, and we get this as our solution. x1 of t is equal to e to the minus 2t, e to the at, here's a, times the initial condition, plus the integral from 0 to t, and here's the convolution. Okay, well, in this case, I know everything in this convolution. x2 of t is this quantity here. Notice x2 at 0 is just a constant, and so I know all of this stuff. I can actually go through and perform the integral, and when I do, then this is what I get. Okay, I get all of this stuff when I perform the integral. So this then is the solution x1. We already had the solution x2, and so this is the general solution to the differential equation for initial conditions x1 at 0, x2 at 0. Okay, so this is the general solution. Now I need specific solutions, and to do this, I'm going to choose the initial conditions to be columns of the identity matrix. So the first column of the identity 2 by 2 identity matrix would be 1 and 0. So here's x1 is 1, x2 is 0. And so when I plug that initial condition in to these equations, I get this expression. Now here's the second column, x1 is 0, x2 is 1. When I plug these initial conditions into these equations, I get this expression. Okay, and so this is the solution when I have this initial condition. This is the solution when I have this initial condition. These initial conditions are columns of the identity matrix. And so, as a result, x of t, the fundamental matrix of solutions, is basically those two columns stacked side by side. The state transition matrix then is x of t, x of tau inverse. So if I take this matrix, then I take a copy of it, substitute tau in for wherever I see t, take the inverse of that matrix, multiply by the original matrix, I get all of this stuff. This is the state transition matrix. So we can actually compute the state transition matrix. And so here it is. Fairly straightforward. But again, this is about as simple a problem as we can get for a linear time varying case. So it's more complicated because in a sense you have to solve the differential equations by hand and then work with it from there. So it's definitely more complicated than the linear time invariant case where we have the nice formula e to the at that we can work with. All right, for periodic systems, so this system is also a periodic system. It satisfies this. And so we can, again, use Floquet theory, blah, 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 Floquet theory. So here's another example. This is also periodic with period 2 pi. We can go through and show that the fundamental matrix of solutions actually looks like this. Okay, after a bit of work, I can go through and show this, the fundamental matrix of solutions. Incidentally, the fundamental matrix of solutions is a square matrix, and it should also be, when you evaluate it at t equals 0, should give you the identity matrix. So that's another thing that should happen. All right. We can now define F to be this matrix, X inverse initial condition X of t. So we actually defined X to have initial condition equal identity. So this, actually, I take that back. This is a fundamental matrix of solutions. It's not the one that has 0 for the identity. So it turns out that, I'm sorry, at 0. It actually has this value at time 0. So in this case, I get this, multiplying it out, I get this expression. So it actually, in this case, happens to diagonalize. And so 2 pi is the period. So we actually have this. And so this S can be written this way. And so we can go through and show that P of t is given by this expression, and X of t then is P of t e to the st. So this is an example that we can show using Floquet theory. All right, simple exponentials. So if A is a projection, so in some cases we can actually get a nice formula for the matrix exponential. In most cases we can't, but in few cases we can. So if A happens to be equal to A squared, that's a projection. Okay, then you can go through and show that e to the at is equal to I plus e to the t minus 1 quantity times A. So notice how simple this expression is. So I'm not actually having to compute e to the at. So the e, the exponential term, actually appears just in the scalar part, right here. Okay. So, but that's because the matrix itself is simple. It is a projection. And in fact, whenever you have a matrix that looks like this, you can go through and show that its characteristic polynomial, or rather, yeah, you can go through and show that its characteristic polynomials have the eigenvalues either 0 or 1. Okay, and so that's part of the reason why it makes it so simple. And so this term is actually the term that's associated with the eigenvalue 0, and this term is the, well, actually the difference is associated with the eigenvalues associated with eigenvalue 1. If A is nilpotent, so that's another case. That is, a to the power n is 0. We can go through and show that the infinite summation for e to the at stops at n. Okay, so we actually, this is just a polynomial in A. And so it's fairly straightforward to compute. We don't actually have to go, so we can actually compute e to the at this way. We don't have to actually go all the way up to infinity to define it. Next, if A is a simple rotation matrix. So how do we define a rotation matrix? Well, here's one way. If you have two vectors whose inner product is 0, that is, they're orthogonal to one another, and the inner products of these vectors with themselves is 1, okay, that is, they're normalized vectors, and they're orthogonal to each other. If I define this matrix, okay, V times U transpose minus U times V transpose, notice that this is a column times a row, this is a column times a row, so this gives me a square matrix. So remember, when you have two vectors, that you have an angle between the two, and so you can go through and show that e to the a is given by this expression. Similarly, if A transpose is minus A, this is the case when you have what's called a skew symmetric matrix. So if you happen to have this condition, you can go through and show that e to the at inverse is actually e to the at transpose. That is, e to the at itself becomes an orthogonal matrix. So if you have A given by this. If A squared is equal to the identity matrix, this is another case. You can go through and show that e to the at is equal to the hyperbolic cosine of t times the identity plus the hyperbolic sine of t times A. So again, this formula is simple like this formula. Okay, so if you have simple examples, and notice here I haven't even said what does A squared look like that does this. Okay, so that's kind of an interesting thing to think about too. What kind of matrix A squared does this? It doesn't have to be in the identity that'll do this. Okay, so but there are non-identity matrices that do this. Well, actually, you can go through and show that a matrix that does this at least a 2x2 matrix that does this has to be singular, which is kind of interesting. Well, anyway. All right, suppose we have this matrix now. If you take this matrix, notice A and B are symbolic variables. I can still go through and do the eigenvector decomposition. And in this case, I will get these eigenvectors. Okay, they're complex. So notice I have a J and I have an imaginary part and a real part. The eigenvalues are like this: A minus JB, A plus JB. Okay, so notice that because your A matrix is real, if I have a complex eigenvalue, I also have its conjugate eigenvalue, and the eigenvectors are conjugates of each other. Okay, so that's the case whenever we have this kind of situation. And so I can go through and show that this now is the matrix exponential. And so in general, notice we will have an exponential term, a real exponential, and then we have this either sine or cosine in here. And so we get complex exponentials coming out. Okay, so whenever you have complex eigenvalues, you will get complex exponentials whenever you have e to the at. So you'll have a exponential envelope to a sinusoid. Okay, so that's the kind of thing that we get whenever we have complex eigenvalues. So these are some of the practice problems.